So as we progress further into the class and breaking down metabolism, today we're going to shift from kind of the making of ATP into what we use as substrates for ATP. So as a reminder, just harkening back to class, when we talk about substrates, what we really mean is carbohydrates, fats, or protein. And as with the lecture, for the most part, we're just going to consider carbohydrates and fats as our substrates and somewhat ignore protein in all of these ATP producing processes. So as we move forward, we're going to talk about how we're able to ultimately determine what substrates we should use and how we measure them, which is a term that we're going to define as the RER. So as we get started, let's introduce kind of the first topic. So RER's respiratory exchange ratio is ultimately determined by fat and carb contribution to energy production. So if we look on the left-hand side of the screen here, what we can see is fat in dark black, carbohydrate in white, and protein in gray, and essentially what percentage of the energy that each of these three substrates are providing. Again, we can ignore protein for this class and for lecture, as well as A, this is kind of complex, and B, provides relatively small amounts of energy as we go. If we look at this, what we can see is the major takeaways from this figure. And I'll note, you don't have to know how to draw this figure precisely. We're just trying to give you a good example. The major takeaway from this is as we look at the percent of carbohydrates and fat used, it is completely variable throughout the day. So in certain instances, right, we'll use a lot of carbohydrates. In other instances, we'll use a large amount of fats. As you can see during sleep, right, lots of fats, less carbohydrates as we work through. So again, just this idea that carbohydrates and fats are used essentially in a very specific manner. Our body has a very good ability to change which substrate it's going to use depending on certain elements. For example, one element might be a meal. So if you eat a high carbohydrate meal, you'll notice that we'll see a large spike in carbohydrate usage here. The idea that in general, if you consume a bunch of sugar, your body will respond saying, well, we now have this substrate in excess, so let's use this for energy production. In something like sleeping, right, and is a good example here, carbohydrates become limited, so we start to deplete our glycogen stores in our liver, which is donating most of the carbohydrate into our bloodstream. And so during sleep period, we get most of our energy from fat. You'll also note in several of these they have an E, which essentially is looking at an exercise session, and that is going to become, again, the focus now as we begin to think about exercise physiology of how do we alter the usage of these substrates, not only throughout the day, but also to provide us with substrates and energy for exercise as we move forward. So first, let's kind of break down the properties of both carbohydrates and fats as we look at them for substrates. So this is hopefully somewhat of a review from a sports nutrition or intro to nutrition class, or you should remember at least the majority of this from lecture as we go through. If we look at carbohydrates, they have a relatively low energy density of about 4 kcals per gram of carbohydrates. On the other hand, fats, these have a very large energy density number. They have 9 kcals per gram of fat. We can think of this in two ways, again, that this can be if you eat a gram of fat, it contains 9 calories, or if you break down a gram of fat, you'll get 9 calories worth of energy. Either way, that relationship maintains whether it's eating or expending it as we go. As a reminder, we can think about this in terms of the lecture and why this number is 9 and why this number is 4. Predominantly, it's because of the number of carbon bonds that take place here. So in general, fats, right, these are usually large numbers between 12 and 24. Evenly numbered carbon bonds that we can break down through beta oxidation, whereas carbohydrate is glucose. It's the only sugar that we can break down. It has 6 carbon molecules, and again, we can really think about energy as breaking those carbon bonds and then using the energy stored in those in order to create energy or energy producing molecules in order to make ATP. If we look at how much energy is stored in the body, in our in our storage of carbohydrates, we have roughly a day's worth, or 2,000 calories worth of carbohydrates stored as glycogen in our skeletal muscle and liver. So in general, a decent amount of calories, but on the larger scale, not that many when you compare it to the amount of calories in our body that we have stored as fat. Anywhere between 50,000 to 200,000 or even more as we think about how many grams of fat we have stored in our body. In general, even people who are, in good shape and lean have 100,000 or more calories stored as fat. So ultimately, carbohydrate can become limiting when we look at it as a storage form, and fat has, of course, no way then to be limiting in any process because we have plenty of energy. I like to make the comment here that even if you don't think you could, each and every one of us could complete a marathon today based on energy that we could provide. Now, notice I didn't say run, I just said complete, because indeed we can produce enough energy from our fat storage and able to make enough energy to be able to complete 26.2 miles. It just might be an incredibly slow 8 to 10 hour marathon, but nonetheless, we have the energy required stored up in our body in order to produce those. We'll look at two more key properties of these. The first is the amount of energy per liter of oxygen that we can produce. We'll look at our number first, so I'll put a star by this. I want you guys to remember these numbers. A, memorize the numbers for the exam, but B, I want you to remember them because we're going to use them here in a little bit later in the lecture. So for carbohydrates, we produce more energy per liter of oxygen consumed than fat. Specifically, 5.05 kcals per liter of oxygen consumed for carbohydrate and 4.7 liters of oxygen for fat. To give you an analogy of what this means as an efficiency thing, I try to relate it to a concept that most people are familiar with, and that's with miles per gallon in a car. So let's say, for example, there was a zombie outbreak in Tyler, Texas, and your job was to get as far away from Tyler as physically possible. You had your tank of gas in your car and you couldn't get any more because people go crazy when we have any type of natural disaster. And so there's no gas. All you have is the number of gallons. Let's say you have 5 gallons that you can use. Would you then take a huge truck which gets 10 miles per gallon, or would you take the Honda or the Prius which gets you 40 miles to the gallon? Again, with the main goal just to say which one gets us farther in this scenario. Hopefully, of course, you're from Texas, so you probably all pick the truck regardless, but hopefully your mind says, well, the Prius makes sense because it is much more efficient and gets us farther in a miles per gallon situation. The same idea we can work through here is our carbohydrate and our fat, with our carbohydrate being our Prius in this example, in that it gets a large miles per gallon. Here again, our units though instead are kcals per liter of oxygen consumed, whereas fat then would be the example of our least efficient vehicle, which is the truck, suggesting that we get 4.7 miles per gallon, again as an analogy, really meaning kcals per liter of oxygen consumed. So again, and the idea is you're going to determine sometimes as you move forward which one of these you're going to use, sometimes based on this principle here. The last thing that we'll look at is the respiratory exchange ratio. The respiratory exchange ratio is 1 for carbohydrate and 0.7 for fat. We're going to spend quite a bit more time on this today, so let's now move into the definition and the calculation of RER. So RER stands for the respiratory exchange ratio. It's calculated, again, during steady state, which tells us that we have an unchanging value of oxygen consumption, and it's calculated here by the formula of the volume of CO2 divided by the volume of oxygen. So as we look at an exercise test, you can pull the one up from last week that's on the screen from RJ, and you can get a quick look at it. Both VCO2 and VO2 are both imprinted in one of the columns. Luckily for you guys, you don't even have to be able to calculate this because RER is already calculated. As we look at RER, we can say that an RER of 0.7 tells us that all fat is being used as a substrate. Conversely, an RER of 1 tells us that all carbohydrate is being used as a substrate. So if we think about this, I like to put this on a continuum. So we have two sides of the spectrum. So we have this side is all carbs, this side is all fat. So this tells us that the RER is 1.0, and this tells us that the RER here is 0.7. So at no point, as we walk through the lecture, should you give me a value that is anywhere outside of this range. So only give me 0.7 or 1 and somewhere in between. Never outside of that. We cannot have respiratory exchange ratios different than 0.7 or 1. Always sandwiched in between. And so we can then look at things similar to this. So as we kind of think about this as a continuum, if we have something that's 50-50 here, so 50% carbs and 50% fats, then that tells us that the RER would be this perfect number that sits right in between, or an RER of 0.85, which again is that number that is right in the middle of 1 and 0.7. So that's the average, and again tells us that we're perfectly split between using carbs and fats. So this is really the scenario I want you to, again, focus on, and as we move forward, a lot of the times we're going to talk about, okay, which way does the RER move? So is it moving from 0.85 closer to 1? So let's say a 0.95, which would again be more carbohydrates than fats, or we can move in the opposite direction of here, which would be maybe a 0.75. And that would tell us that we're using more fats than carbs. So again, this is really what I want you to kind of understand and focus on in this lecture is which way are we going? So kind of think about that middle being 0.85. If we start using more carbs, we move to 1. If we start using more fats, we move to 0.7, and anywhere in between. Now you may be thinking, why is this so confusing? Why do we have numbers of 0.7 and 1? I'll say you don't have to memorize this, just demonstrating that these numbers make sense from a biochemistry perspective. So here's our formula for glucose, C6H12O6. As you should know from class, again, when we have a 6 carbon molecule, we produce 6 CO2s. We also consume equally 6 oxygens. Therefore, our RER is 6 divided by 6, which tells us our RER is 1.0. In a fat, again, you should see here's a 16 carbon fatty acid. We should immediately know we make 16 CO2s in this scenario. However, we consume 23 oxygen. Again, here's that efficiency number coming out as we talked about, where there's more oxygen needed to break down a fatty acid. So here's an example, 16 divided by 23 now gives us 0.7 and sets us up to understand that this number is, of course, the bottom of our range. So again, as we move forward and in the next video, what I want you to start to do is really start to hone in on, okay, what's a reasonable value for this? If we're using mostly carbs, what's a reasonable value? If we're using mostly fats, what's a reasonable value? If we're using somewhere in between or perfectly 50-50, what value would that give us? As we move forward, that's really what I want you to take away as we move into exercise in the next video.